Welcome back. Today we're going to talk about graphical summaries of data. We've been talking about categorical variables and quantitative variables, but today we're going to look at the types of graphs and charts that we can put them in so that we can help interpret and see what's going on with data. Our goal is to look at the center, the shape, the spread, and the variability or the spread or variability of these types of data, of this data, and these types of graphs are going to help us do that. So the first one that we're going to talk about is a pie chart. And if you remember seeing a pie chart, when from young ages, right? So in here are going to be our slices of pie, and each of them is going to represent a percent of the data, right? And so these percents of the data, we call them the wedges. The wedges are percentages of the data. And all of the wedges add up to 100%. So you have to represent all the data, and it has to be equal to the full circle, which is 100%. Bar graph. A bar graph and a pie chart are ways to represent categorical variables. So we're talking about different categories, and what percentage of the data means, if you've got 10 dog owners and 2 of them own Labradors, so 2 of 10 would be 20%, so one of the wedges would represent 20% of the data. When we look at a bar graph, because they're categorical, they're going to be different bars, obviously, and there's going to be space between them. And the space between them denotes that we're not talking about continuous variables, right? We're talking about the bars are, again, percentages of data. And our bars are apart. In addition, let's say that we've got bars that are ordered by frequency. So for example, let's say instead of having, short, taller, shorter, tallest, I put them in order like this. And I had like my tallest one, then my next tallest, and my next tallest, and my next tallest. And I had to rearrange the bars. This is called a Pareto chart. So it's a special type of bar graph that's ordered by frequency, so greatest to least frequency. Another hallmark of these, when I've got my category here that's the tallest, it's called the modal category. It's called the modal category because the mode is the most common, or the most common data point. The mode would be the tallest. Okay? Talking about quantitative variables. So quantitative variables are ones that are measured by numbers, right? And so when we're talking about quantitative variables, we're talking about asking someone's height, someone's age, someone's shoe size, things like that. When we use a dot plot, we've got a line with distinguished variables. And what we can do on a dot plot is we put our observations dots above a given value. And with a dot plot, what we see is each of these dots represents an observation. For example, if you asked me my height and I said I'm 6'3", that would be one of the heights on this chart. Well, I would be one representative of one dot. And the bottom is in regular intervals. So you want to make those breaks regular. And each observation is one dot. Stem and leaf plots. Stem and leaf plots work like this. My stems go over here. And my leaves go here. Stem and leaf plot looks like this. Let's say I've got 7, 8, 9. I'm going to make this really easy. So I'm going to go 6 and 9. And then I've got 0, 0, 1, 2, 5, 6. And this would be like 1, 2, 3, 4, 5, 6. Well, the way that this works is it's a way to organize data to see how many values fall in each category. So for example, I've got to have a key at the bottom. So if I've got this 9 and this 2 together, that would be 92. So like this list over here is 76 and 79 representative. Okay, our stem and leaf plot works like this. Typically what you do is the leaf becomes the last number. Or the last place value. Okay? And so, if you'll notice, my stems go from least to greatest. And my leaves go from least to greatest. That helps me find data. I don't want it all mixed up. It's going to help me find the data. Okay, and so if I have a lot of values, sometimes what I might do, or I have larger values, I could also have something like this. Stem and leaf. I could do it like this. 20, 21, 22. I have like 1, 2, 3, and then I might have 6, 7, 8, 9. And I would do something like this 22 and this 8 would come together. That would be 228. So my last digit became my leaf. I must have a key. I must have a key. What does my key look like? My key would look something like this. It would look like this. 22/8 equals 228. Got to have a key down there so someone that looks at your stem and leaf plot knows exactly what they're looking at. Okay, histograms. In a histogram, I've got my relative frequencies. Meaning compared to everything else, all of the data, my relative frequencies would say I've got 5% of my data falls into this category. 5% of my data falls in this bin, right? Relative frequencies of quantitative data. And my histogram looks like this. I've got my frequency over here. And I'm going to have my bins down here. And my bins are going to be divided into these intervals. So I'd have something like this. 0 to 4, 5 to 9, 10 to 14, 15 to 19, 20 to 24. And so my intervals have to have endpoints. Okay, so 0 to 4 falls in this bin. And so on my graph, I'm usually going to have 5 to 10 intervals. And so what my my histogram of my frequencies actually looks like would be something like this. And what you notice is there are no spaces here, right? So in this one, there's no space. So what we need to keep in mind is if a value falls on an end point of an interval, it's usually going to go to the left. All right. I'm going to skip over our example problems for right now, and we're going to go down to the shapes of distributions. So scroll through your notes to shapes of distributions, then we're going to go back and we're going to look at a couple of examples. But when I'm talking about shapes of distributions, I can have two different things. I can have a unimodal or a bimodal. Now, these aren't the only two shapes of graphs. You could have evenly distributed or symmetric. And so we can have symmetric could be unimodal, or symmetric could mean all of them are the same. Unimodal means there's one mode. Bimodal means there's two modes. The graphs for these would look something like this. Let's say I've got a histogram here, and I can tell that it's a histogram because my frequency is on the side here. And my frequency here is going to have data derived from my data points here. So 90, 95, 100, 105. And my data is going to look something like this. So I'm going to have and it's unimodal because I see there is one mode. And so I've got one mode. It's obviously denoted by this largest bar here, which tells me that that data value has the highest frequency. When I've got bimodal, I've got two modes. And so what my data might look like is this. I'm going to use actually a different data set. And these are just potential numbers, right? So what I see here is I still have my frequency on the side. But what's going to happen with my data values is this. I have two modes. So in this case, now what might possibly cause this to happen? Well, obviously, let's say you take a pre-calculus class or an AP Stats class, and I say, hey, how old are you? You're going to have maybe some people on the lower end, maybe some people on the higher end, but you're going to have most people kind of around that same age of like 17 years old per se, maybe 18 years old. So what might I have with two modes? I might have a data set that has, I don't know, males and females as part of it, and maybe the males and the females have very distinct areas in that data, right? Or I might have two classes of students, and one is predominantly sophomores, one is predominantly juniors, and I'm asking all of my students, and they fall into two distinct categories. And so I could have unimodal or bimodal data. One of the things we're going to talk about very in depth is the shape of data. Okay, so when we're evaluating data and we're talking about comparing data or we're talking about describing data, one of the biggest things, and I'm going to put a bunch of stars around this, is you need to be able to talk about the shape and look at the shape and determine what is going on here. And by shape, we're talking about three different possible ways of looking at this. And our shape is going to be determined by, obviously, the shape of the data. And when I have data like this, we're going to look at where the tails are, right? So the tails of this data, so it's got this peak in the middle, and it's got two tails that kind of go off to the side. This kind of data is known as symmetric because it's a mirror image, right? So I've got this, and one side is the same as the other side. What could also happen is I could have data that looks like this, right? It's shifted to one side. And so an example of this kind of data might be like lifespans, right? And so there's some people who live for a really long time. There are a fair number of people who don't live all that long, but there's kind of this cluster of like 60, 70, 80 years old where a lot of people live to be those ages. The hump is to the right, the tail is to the left, so this is called skewed left. Skew describes the tail. So the other option would be to have a tail to the right, so this one would be skewed right. Now an example of this might be incomes, right? There's a fair number of people who have this type of income, right? 50,000, whatever, 40, whatever it is, 100,000, whatever you want to call it. And as we get off into the higher incomes, it kind of tails off. All right, and so when we talk about shape, we could say things like this. Appears to be skewed left, slightly skewed, etc. The thing about statistics that we really need to hammer home is we are looking at data and we're making some generalizations, and so using LY words, slightly skewed, fairly skewed, very skewed, right? So we're looking at words that are going to describe the shape of the data. Something else could happen. We could have data that sort of looks like this. Where there's a big old gap. One of the things we're going to talk about in the later section is the concept of an outlier. An outlier, there's a technical way to find it. It's based on the median, it's based on the quartiles, it's a calculation to determine, is this an outlier? But what we would say is, if we see this gap in this data value, we would say that this is a possible outlier. Right? It's a possible outlier. What commitment have we made there? Well, we're not saying it's an outlier. Outlier is a mathematical computation. Is it an outlier or not? But to say that there's a possible outlier, that's true. Okay? To say that there's a possibility that there's an outlier over here. Okay, so this is appropriately vague. Okay, we want to say a possible outlier because it's not technical in nature. Okay, so now let's go back and do a couple of examples to help us hammer home these ideas of looking at data and what is an appropriate data display and what are some of the things that are going to go into evaluating data displays once we have them from our data. So let's go ahead and look at a couple of examples. What we have here is a list of the sodium values in a given number of cereals. And what we're going to do is we're going to make a stem and leaf plot of the 20 values. I'm going to show you about 3 ways to do this, but the first one is going to be the long way. So let's talk about stems and leaves. So I need to make a big chart here, right? So my stems, notice I've got a 0 here, and so just to represent that, like my stems and my leaves, I'm going to have my hundreds place or my tens place here, and just kind of watch as I go down here, right? 4, 5, 6, 7, 8, 9, 10. So this would represent, like if I had 100 here, it would be 100 and a 0. That would a 10 and a 0 would be 100. And so, but I've got to keep going because I notice I also have this 340 here, and I think that might be the largest value. It is. So I've got to go all the way down here. So 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Wow. There's a long list. 31, 32, 33, 34. And what you're going to see is I'm going to have this really big stem and leaf plot, but I'm going to show you a couple ways to cut it off or to truncate it that are going to be meaningful as well. But let's do all of our work here to begin with. I'm going to draw some lines here. You don't necessarily need them all the time, but sometimes when you're drawing a data display and you don't have the benefit of doing it on a computer, you've got to really make it clear. And so I'm going to draw these lines through so that when I put my leaves in, you can actually see what I'm talking about. So I like to go down the list. So I already put in 0. 340 is going to be down here. I'll put a 0 there. And I'm going to do 3 at a time. 70, 140, 200. 70, 140, 200. Okay. 180, 210, 150. 180, 210, 150. 100, 130, 140. Okay, so now we have 2 140s. 180, 190, 160, 180, 190, 160. 290, 50, 220, 290, 50, 220. Okay, 180, 200, 210, 180, oops, 210. Okay, so now kind of look at this and see what we've got going on here. Well, so I've got 3 values at 180, right? So that one seems to be the mode. I've got a bunch of other values stuck in here, but what's the problem with this chart? I got all these areas where there are none and this huge long stem and leaf list. So what are some ways that we could possibly fix this? Let's take a look at those. So one of the ways we can do this is we can truncate the stems. And by truncating the stems, oh, I forgot. Hold on. I got to finish this. I've told you that one of the keys to a stem and leaf plot is to make sure that you have a key. And so what I can do is I'm going to take this value here and I'm going to make a key. 34.0 equals 340. Okay. Too close. 34 slash 0 equals 340. Okay, so the stem is important because it tells us exactly what's going on. A couple of ways to do this where it would be shorter, and we're not doing it shorter for shorter's sake. We want to condense the data to make a meaningful data display, and I'm going to do two truncated examples here. And what you're going to see is that one is more maybe meaningful than the other. So I could drop the zeros. So I could say that 3-4 equals 340, meaning every single zero gets dropped because the last digit is all zero. So what if I made my stems? What if I made my stems 0, 1, 2, 3? And instead of taking my data and having it be where 0 is my leaf, what if my tens place was my leaf? And so I have a data value that's 0, right? So I've got 0. That would still be 0, 0. 50 would now be 0, 5. So 50 would be 0, 5, and because I've dropped the 0, 0, 5 would be representative of 50. I also have a 70, so I put a 7 in here. In my next one, I'd have 1, 0, which would be 100, but I'd also have a 3, 4, 4, because 1, 3 would be 130, right? 140 would be 1, 4, so I've got 2 of those. And then I go down the line, 5, 6, 8, 8, 8, 9. And 1, 9 would be 190, right? So then in my 200s list, I've got a couple 200s right here. I've got a 210, another 210, a 220, and a 290. In my 300 level, I've got 3, 4. So my key would be 3/4 is 340. That's a way to truncate it. Now, check it out. All of my data gets really lumped together. So obviously, I've got my most stems and leaves, or my most leaves in the 100th level. Well, sometimes that's meaningful, sometimes not. Like, there's a big difference between 100 and 190, right? And so one of the things we could do is we can go split stems. And that would be where the first stem represents 0 to 4. Second stem is 5 to 9. Here's what I mean. Another way to truncate this would be to say my stems and my leaves could look like this. I could put in a 0 and a 0. I could put in a 1 and a 1, a 2 and a 2, and a 3 and a 3. Well, if I split my stems, check it out. So I'm going to have this one goes 0 to basically 40. And so how many values do I have in there? I only have 1. But in my second stem, this one goes 50 to 90, right? And so I'd have a 5 and a 7 in there. I split those stems, and all of a sudden I can see that half of, by making it half, which data values fall where. In my hundreds level, I'm going to have 0. I'm going to have, consulting my notes here, 3, 4, and 4. Okay, so 0, 3, 4, 4. This one would have 5, 6, 8, 8, 8, and 9. My 200th level, I'd have 200, 200, 210, 210, 220, 290 would go here. And then 3, 4 would be 340. I don't have anything down here. Can't put anything. I can't put a 0 because I don't have a 3. Another 300 like that. And so still my key would be 3-4 equals 340. Okay, so that's how the split stems would work. You can divide the category into first half of data, second half of data. Let's look at another example. TV watching. Okay, so TV watching, the 2012 General Societal Survey asks on average day, about how many hours do you potentially or personally watch television? Figure 2.5 shows the histogram of the 1,298 responses. So they've got some data over here represented in a histogram. When we look at this histogram, what do you immediately notice, right? So we notice that we've got a skewed right. So not a whole lot of people watching 24 hours a day of TV. Somebody said they did. I don't know what that means. But we've got most people kind of sitting around 2 hours. These generalizations are hugely important. And one of the things that we're going to talk about in this example is the importance of context. When you answer AP questions, you have to provide context. And so for years, your teachers have been saying, use a full sentence in your answer, right? So answer in complete sentences. Well, this is a case where you must do that because you can't just say, so let's look at the first question. What is the most common outcome? You can't just say 2 hours. Even though when you and I are talking, right, I might say, hey, which bar is the tallest? Or what was the most common outcome? You say 2 hours. That doesn't provide context. And so what they're looking for is you to reiterate what's going on here. So in answer A, you need to say something like this. The distribution of TV watching has a mode of 2 hours. Okay, here's my context. Distribution of TV watching. You could say 2 hours and you could be talking about running a half marathon, right? And so this right here is a fact from the graph. So you provided context, you provided a fact from the graph. That is hugely important. You have to provide the context. When we look at B, what does the histogram reveal about the distribution of TV watching? What we're saying is, what is going on here, right? What is going on in this distribution of TV watching? What does it reveal? Well, kind of like you and I generalized here just a second ago, there is this skewed right? So you could say something like this. Most people, not committal, most people watched between 0 and 4 hours per day. Is that true? So 0 to 4, yeah, most of the people fall in that category. Very few watched more than 8 hours per day. Hours of TV per day. Context, context, context. So even here I should say hours of TV because that's my context. They did 0 and 4 hours of what? Gardening, cooking, eating, whatever it is. It's got to be specific to the problem. Watching TV, watching hours of TV per day. Okay? What percentage of people reported watching no more than 2? No more than 2 means 0 to 2. So if we look at this, here's my percentages, right? So 0 hours, that's about 7. 1, that looks to be about 19. And 2, that looks to be about 25. So when I add up those percentages, it would be 26 plus 25. We'd say about 51% of respondents reported. Important the way you say that. You say this is what they reported, not necessarily what they do. What they reported was 51% of respondents reported watching no more than 2 hours of TV per day. Again, context. Respondents that reported, not they did or they didn't, they reported that they watch no more than 2 hours of TV per day. That's context, 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 guys, okay? So important to include the context in your answers.